In this example, we want to show that vector u is equal to vector v. And to do this, we're going to use our definition of equivalent vectors, which is that the vectors have to have the same magnitude and they have to be going the same direction. So let's first of all find the magnitude of vector u. Remember, to find the magnitude, it's the same as using the distance formula. So we're going to say x2 minus x1 squared plus y2 minus y1 squared. And that's going to give us the square root of negative 2 minus 1 is negative 3, squared is 9, 3 minus 1 is 2, squared is 4. So the magnitude of vector u is the square root of 13. Now let's find the magnitude of vector v. We're going to do a similar thing. x2 this time is negative 6 minus negative 3 squared, plus y2 is 2 minus y1 is 0 squared. Negative 6 minus the negative 3 is negative 6 plus 3, which is negative 3 squared, which again is 9. And 2 minus 0 is 2 squared is 4. And so we get the magnitude of vector v is also the square root of 13. So these two vectors do have the same length, they have the same magnitude. To find that they have the same direction, let's find the slope of the line that ray PQ is on and ray RS is on. So if we're going to find the slope of PQ, remember that the way you find slope is equal to y2 minus y1 divided by x2 minus x1. So y2 would be 3 minus y1 is 1 over x2 is negative 2 minus 1. And so we get 2 over negative 3 is the slope of that line. Now let's find the slope of RS, doing a similar thing. This time y2 is 2, y1 is 0, divided by x2 is negative 6, minus x1 is negative 3, and if we subtract, we get 2 over negative 3. So we have the same slope, we have the same magnitude, so the two vectors are indeed equivalent. You could also think about this another way. If you were to write vector u in component form, vector u in component form would be negative 2 minus 1, which would be negative 3, and 3 minus 1 is 2. And then if we were to look at vector v and write it in component form, we would have negative 6 minus a negative 3, which is negative 3, and 2 minus 0, which is 2. And so both of these vectors in component form are negative 3, 2, so they should be equivalent to one another. That means that they should look like any vector that starts at the origin, goes left 3, and up 2. So any vector that has component form negative 3, 2 should be equal to any other vector that has component form negative 3, 2. And if you were to go back and actually geometrically look at these vectors, vector P, point P is at 1, 1, and Q is at negative 2, 1, 2, 3. So that vector is parallel to and equal to the component form vector negative 3, 2. And if we went back and looked at a vector RS, R is negative 3, 0, and S is negative 6, 2. So again, we get a third vector that is parallel and equivalent in length to the other two vectors.